introduction to section 1.5, two things: elementary matrices, and then secondly, a method that we call an algorithm for finding A inverse. I won't be able to get to finding A inverse, but let's talk about elementary matrices. There's a classic theorem in this section for matrices. We started in this section, and then as we go on throughout this course, we add other equivalent statements to it that I have, I think, rightly called the monster theorem. And it'll be a monster theorem. You know, Godzilla was a little lizard, and then nuclear waste and off the outskirts in the oceans of Japan got to him, and he turned into this very big, huge, gigantic monster. Godzilla. Right? It's my favorite monster when I was a kid. Godzilla. Anybody remember? Nobody remembers this dude, but when I was a kid, we used to watch him too. Gamera. Anybody, you remember Gamera, the big old target? Oh, that's cool. And a little kid used to ride his back and stuff. It was the stupidest thing, right? Okay. Come on, dude. Okay, so so let's define an elementary matrix. First, recall the elementary row operations. There were three, right? We said that you can interchange rows. You can multiply any row by a non-zero scalar, and then you can add a multiple of one row to another row. So those were the three elementary row operations that we had from ago, and I got those right there, those three statements. Just recall that. So if you take the identity matrix, that's the matrix that has along the main diagonal ones and zeros everywhere else. And if you perform only one elementary row operation on the identity matrix, we call that matrix an elementary matrix. Right? Makes sense, right? An elementary matrix comes from basically the identity where you perform only one elementary row operation. So it's a very simple matrix. So look at these examples of elementary matrices. See that first matrix with 1, 0, 5, 1? All we've done here was to multiply a factor of row 1 plus row 2. We said 5 times row 1 plus row 2. Right? Look at the second example. What they did here was to interchange rows 2 and 3. That's only one elementary row operation. So this is the elementary matrix. This is the first one's the elementary matrix. And then this last one, well, how do they get that 7 there? Exactly. Again, that's an elementary row operation. So if you perform onto the identity matrix only one elementary row operation, we call that matrix an elementary matrix. So there's a definition there for the elementary matrix. It's a square matrix that can be obtained from the identity matrix by performing a single elementary row operation. Theorem: every elementary matrix, is invertible, and the inverse is also an elementary matrix. Very basic, but most profound. Every elementary matrix is invertible. Because remember, the identity matrix is invertible. So if I perform an accurate elementary row operation to the identity matrix, then obviously that result is also invertible. And that result, the inverse that you get, is also an elementary matrix. Now here's the big theorem. How did that get knocked off there? I call this the monster theorem. If A is a square matrix, then these following terms are all equivalent. as we go through this course, we're going to add to these terms. So here, if I know one is true, then all the rest of them are true. So if A is invertible, then the system AX equal to 0 reduces to the trivial solution. If I know that A is invertible, then the reduced row echelon form of the matrix A is the identity matrix. And we're going to see that in this algorithm to try to produce A inverse. And then lastly, A is expressible as a product of elementary matrices. Now when we come back on Monday, I will prove this, and then afterwards we will look at some problems, like some 3x3 matrices, and find their inverses. Okay? Any questions? Thank you.